Okay, this is lecture 1. This is an introduction to programming. So computers are everywhere. You're watching this video in front of a computer, but if you look around closely, you'll realize that there are other computers all over the place. These computers may not look like the laptop or desktop that you're looking at right now, but they are indeed computers. Maybe the most obvious example is your cell phone. That is a fairly sophisticated computer. Your thermostat in your house might be controlled by a computer. Your car probably has several different computers in it controlling the engine, the airbags, the heat and air conditioning, and more. And these computers probably need to communicate with each other. Your dishwasher might have a computer in it. An elevator has a computer controlling it. An airplane has many computers in it, and so on. I could almost go on all day about how many computers there are around us. Now, computers need software to tell them what to do. Computers themselves are not terribly interesting to me. I'm the kind of person who rarely will crack open my computer case and mess with the hardware inside. What I find fascinating is creating the software that controls the computer. So a computer programmer, another name for this type of person would be a software developer or a software engineer, writes software in a certain programming language, and that software controls a computer. And we're in a computer science course. Computer science is a funny name for this discipline because computer science is largely about creating software. We don't really learn that much about creating computers. Okay, it turns out though there is a great need for professional software developers. There are many very high-paying jobs out there that if you can do it and you enjoy it, and it's what we're going to find out is not everybody can do it, and of those who can, not all of them want to do it professionally. But if you can, there are many great opportunities out there. What some of you may find out, though, is that it's not for everyone. Some people find programming really frustrating and tedious and hard. But other people, like me, feel like it's one of the most challenging, fun, and interesting endeavors that humans can do. Now, I also happen to find it frustrating and tedious and hard sometimes, but the good parts of it kind of really make it fun for me to do. Okay, so let's talk a little bit about the computer. Computers really are quite limited in what they can do. They can really only do simple arithmetic, compare numbers to each other, and move data around in different places. Let's talk about arithmetic. You can ask a computer to sum the numbers 1 and 2, and it will tell you the sum is 3. This is not a magic process. It's all fairly mechanical. If you look at the actual hardware inside a computer. In later courses, we will maybe look at some of that hardware. We'll look at how that works. The computer can really only add, subtract, multiply, and divide numbers. And I'm guessing you can do these things too. Computer can compare numbers to each other. You can ask a computer if the number 5 is less than 6, and it will tell you, yes, 5 is less than 6. And you can ask the computer if 10 is greater than or equal to 20, and the computer will tell you, no, that's not true. Okay, the computer can also move data around to different places. So data is what it sounds like. It might be, a person's hourly pay, a person's number of hours worked, a state tax rate, a federal tax rate. These are all things that can be manipulated to produce useful information. So that's what data is. Data is manipulated to produce useful information. Shortly we're going to talk about the different places that data can live, but you probably already know something about these places because you know a computer has a hard drive and a memory. And the computer can move data from one of these places to another, and even different places within the same component, let's say memory. Okay, so basically the computer can do the same things that a typical 10-year-old can do. Right? Arithmetic, compare numbers, move data around. But the computer has some advantages over the 10-year-old. The computer will never get bored, or complain, or ignore you, or be wrong when doing any one of these calculations. 10-year-olds will do all of these things. And the computer can do these things incredibly fast. So for example, almost all computers can perform arithmetic on two numbers together billions of times per second. Okay, so I talked about adding numbers. Well, the computer can add two numbers, several billion times per second. That's pretty impressive. Now, a computer program is a set of instructions that tell the computer exactly what to do. All programs are mostly made up of these three operations discussed above, right? Arithmetic, comparing numbers, and moving data around. So think about all the programs you use every day. Most of the things I do nowadays are in a web browser. So I might look at Facebook or do a Google search or Twitter. You might use a word processor, you might use a spreadsheet. All of these, if you boil them down, they're really just combinations of those three basic operations. Okay, so you do have to be pretty good with numbers, but you don't really need to have an advanced mathematics background. In fact, if you have the background of your average 10-year-old, you'll probably be fine. Now, of course, computers can be programmed to do advanced math, but everything the computer does really boils down to doing simple things with simple numbers. Okay, so let's talk about writing programs. To write a program, there really are three different phases. Okay, the first is analysis. This refers to analyzing the problem to be solved in order to make sure that you, the programmer, understands what the customer wants the computer to do for them. Our customers are the ones who pay us to write code, so they don't have to learn a programming language. These customers will eventually be the users of the program. I might refer to users or customers in these lectures. They basically mean the people who are going to be using our programs. All programs create something useful for their users. Otherwise, why would you use a program if it didn't provide something of value to you? Okay. If the programmer does not understand the customer's problem, then there's no way they can write a program to solve that problem. That's why analysis is so critically important. And it turns out this is a really surprisingly difficult thing to do because our customers know that they want something, but they can't really tell you exactly in excruciating detail what they want built. You have to work with the customer to discover the program that they want built. Okay. One must also understand the inputs to the program and the expected output. Okay, so we can think of a program kind of like a black box, where some things are going to go into this black box and something is going to come out of it. Okay. So when analyzing, a programmer needs to know where the inputs are going to come from and where the output should go. So the inputs to a program might come from the user at, say, a keyboard, or maybe a gamer using a game controller, or maybe a bank customer at an ATM. Okay, the output, well, that might go to a computer screen, it might go to a database, it might even be the input to another program. So if this is program 1, we might have another program, maybe program 2, which has some input and some output. And that might feed into another program, program 3. So there are inputs, there are outputs to these programs. We really have to understand what the inputs are and what the expected output is for every single program that we write. Okay, so analysis is about understanding the problem the programmer is going to solve. Okay. Next is design. And designing is all about problem solving. Okay, so I like to say computer science or computer programming is really about problem solving. After you have identified the problem in the analysis phase, you have to come up with a plan to solve it in the design phase. And one comes up with a solution by developing algorithms. And an algorithm is really just a fancy word for a plan, how you're going to solve a particular problem. We come up with algorithms all the time. Okay, so let's create one right now. So imagine this is our problem. I'm going to say a bunch of numbers out loud, and your job is to find the largest of those numbers. Okay, that's the problem. The inputs to this algorithm will be the numbers that I say out loud, and the output will be the one number that is largest. Okay, so I want you to play along at home here. Take a few seconds to get ready, and I'm gonna start saying some numbers, and I want you to tell me what the largest number is. Okay, we ready? 17, 21, 12, 5, 14, 31, 9, 14, 17. Okay, so I'll ask you, what is the largest? And I know you all got the right answer. It's 31. So how did we all get the right answer? I'm sure every single one of you got the right answer. Well, we used an algorithm. Now this problem was simple enough that we probably didn't even have to formulate the algorithm consciously. Our brains came up with it without much effort. And that was very nice of our brains to do that, I think. So here's one algorithm. So in our brains, we carved out room for we carved out a little bit of space inside our brains to hold the largest number so far. So I'm going to draw a little box here. And let's pretend this box was in our brains. Okay. Now the first number I said was placed inside that space. So the first number I said was 17. So we put that value inside the box. Then we set aside room for another number, which is the current number. So there was another box. Again, these are in our brains. Okay, and every additional number I said out loud was placed in there. Okay, so the second number I said, for example, was 21. Okay, the next step in our algorithm was we compared the current number to the largest number so far. Okay, so we looked at 21 and compared it to 17. If the current number was larger than the largest so far, then we stored what was in the current number box into the largest so far box. Right, so since 21 is in fact greater than 17, we wiped out that value and put a 21 there. Now if the current number was less than or equal to the largest number so far, we didn't really do anything. Okay, there was nothing to change. If our current number was 2, 2 is not greater than 17, so we didn't really have to do anything. Okay, and then next we repeat these steps as long as there are numbers being said out loud. So every time I say a new number, we'd wipe out the old one, put the new number here, compare it with the largest so far, and maybe put a new value inside the largest so far. Okay, we're going to repeat that process as long as I am saying numbers out loud. And the last step is to output the largest number so far. So whatever is inside this box, when I get done saying those numbers, that's the largest number so far. So notice the similarity in these actions to the one I said a computer can do. Right? We were comparing numbers and moving numbers around. It really was pretty simple stuff, right? This is not the only way to solve the problem, though, and some of you may have done things slightly different. Another algorithm might be to first write down every single number that's said out loud on a piece of paper, and then repeat this process until there are no more numbers, and then go through all the numbers from the beginning and compare them against the largest so far. If one of the numbers on the sheet of the paper is larger than the largest so far, we store it. Otherwise, we go on to the next number. And then again, lastly, we output the largest number so far. Okay, so there's two algorithms there. The one where we just had the two boxes in our brains, and the other algorithm where we used a piece of paper to write down some numbers. Both of these algorithms solve the problem, but they do it in slightly different ways. So I might ask, well, is one of these algorithms better than the other? Now it's hard to say that one is better than the other with only a few numbers. However, if I was going to say, let's say, 10 billion numbers out loud, then I definitely think the first algorithm is better. The second algorithm requires that you write down all the numbers, and writing down 10 billion numbers would require a lot of resources, a lot of paper. Okay, we'd be killing a lot of trees. The first algorithm requires fewer resources, just those two little slots in your brain. Now, when you solve this problem, I'm guessing most of you probably did not write down all the numbers, but maybe some of you did. The second algorithm requires quite a bit of paper and pencil lead, and the cost of those additional resources can add up, especially if we're talking about 10 billion numbers. Okay, that might require quite a bit of paper in order to write all those numbers down. Now, in later courses, we're going to learn that the two most important resources when we talk about computer programming are computation time, or processor time, and memory space. Okay. When coming up with solutions to problems, we'll often need to minimize the use of one of these expensive resources. Okay, one last word about design. Okay. Coming up with these solutions really is a creative activity. Now, I like to tell people that the best software is not written by the smartest people. It's really written by the most creative. Now, there's a stereotype that computer nerds are super smart. It certainly doesn't hurt to be smart, but I would take a creative person over a purely smart person any day of the week. And many of the best programmers I've known are either musical or artistic. Okay, they're creative people. Okay, next comes the implementation. Okay, so the implementation is the translation of your design into a programming language that the computer understands. And this is a fairly mechanical and not very creative process. The creative part of programming is really independent of the programming language. Okay. Now, doing this translation from your design, from your solution into an actual programming language, can be frustrating. Because we're going to need to learn a new language, one that can be read and written by a human, but also understood by a computer. Now, maybe you've learned a foreign language before. You know that learning any new language is challenging. It's made even more difficult because the computer cannot really infer what we really mean like another human can. Right? So if I tell a human to go open the door, the human infers that what I really mean is get up from your seat, walk over to the door, place your hand on the doorknob and twist, push the door until it's fully open, then stop pushing before you slam it into the wall, then release the handle and move away from the door so somebody can get in or out. Okay. So just that one simple command, open the door, when you say that to a human, the human infers all kinds of additional instructions from that. Humans are much smarter and much more sophisticated than computers are. A computer would not see any of those missing steps from the instructions, and certainly would probably not be very good at opening doors. The computer will do exactly what we tell it to do, no more and no less. So we have to be very careful about how we communicate with it. Now in this class we're going to be communicating with the computer using a programming language called C++. There are many programming languages in use today. C++ is just one of them. Most languages have a niche that they fill for programmers. And I expect that if you continue to take computer science courses, you're going to learn several different programming languages. Now, the C++ programming language is a set of rules, symbols, and keywords. And most computer programming languages are made up of these things, although they're slightly different rules, symbols, and keywords. Now, C++ has about 80 reserved words or keywords in it. These are special words that have meaning to the compiler. Of those 80, though, in this class, we're probably only going to use a dozen or so. Okay. So when I talk about learning a new language, it's really a small language, only a dozen words in it, but they're very powerful words. Okay. What we're going to do is we're going to write code in C++ in these text files, and we're going to send those text files to another program called a compiler. And a compiler is a program that reads in instructions in a computer programming language and checks to make sure we haven't violated any of the language's rules. And then it translates our code into something that computer's processor understands. So your processor doesn't know C++, it knows this thing called a machine language. And a machine language is a set of ones and zeros that instruct the computer to do one of the three things mentioned above: arithmetic, comparison, or moving data around. The machine language is not easily read or written by a human, so more English-like languages like C++ were created so that we didn't have to deal with ones and zeros. And these pieces of software called compilers, they translate our C++ code into machine language. This makes it possible for there to be many different programming languages. Like I said, C++ is just one of them. As long as there's some piece of software that will translate a human-readable code into a machine code, then we can have many different programming languages. You might wonder why we have more than one programming language, though. But then I would ask you, well, why do we have more languages than English? Right. It's a little bit hard to explain why this is so to a rational person. Right. So why not globally? Why don't we all just speak English? Well, I guess it's true that we don't need more than one language, but for historical reasons and to account for personal preferences, we have multiple languages. And the same is true of programming languages. Okay, so I'm going to finish this lecture by taking just a very quick look at the program that will find the largest of a series of numbers. Okay, and I'm not going to spend a lot of time on this. We'll talk about the exact syntax of what's going on here in a second. But let me start by running the program. And it says enter in a number. I'm going to put in the exact same numbers. 17. And it says, would you like to enter another number? Yes. 21 was the next number. Then we had 12, 5, 14, 31, 9, 14, 17, and now when it asks do I want to enter another number, I'm going to say no. And it tells me the largest number is 31. Okay, that's just what I was expecting. Okay, so this is that program written in C++. Okay, this stuff at the top allows us to write to the screen. Okay, this thing here, this is called the main function. This is where all programs start inside a function called main. Okay, remember I talked about carving out little chunks in your brain? Well, this is how you carve out room in your memory, your computer's memory, to store numbers. So we have one called current number and largest number so far. Here's another basically a little box that controls whether we want to enter in more numbers. Okay, and then one of the things I do here is I store a really small number in the largest number so far. That's my first step. And then as long as the user wants to enter in more numbers, we're going to ask for a number, and someone typing at the keyboard, whatever they type in the keyboard is going to be stored in there. And if the current number is ever greater than the largest number so far, we're going to take the current number and put it inside the box called largest number so far. And then we're going to ask, do you want to continue? And if they say yes, what we're going to do is we're going to jump back up here. And if they typed in a Y, then we're going to do this whole thing again. And we're going to repeat this process until they say no, at which point we're going to print out that the largest number is inside the box called largest number so far. Okay, so don't worry if you don't understand every single piece of this right now. We're gonna talk in great detail about all these little things coming up in the next couple lectures.